Okay, so it's an enormous pleasure for me to be here. Also, very sentimental occasion. It brings back a lot of memories of my time with most of the people up here. We had very productive, very affectionate meetings, and it also made me think a bit about Abraham Robinson. You know how our group at Yale, for example, would have been had he survived. And I find it hard to imagine, to believe it is the truth that when he died, he was, I think, about 30 years younger than Jim and I are now. You know, what a loss that really was. Anyway, let me get right to the point. I want to ask, could I have the next slide, please, Roman? Yeah. What is special about Jim? When I admire someone, I tend to tell others my feelings, almost always. I often told others how much I admired Jim. I quickly came to see that his sunny modesty and relaxed manner, which makes his company so agreeable, conceal exceptional, oh dear, something has jumped already. That's all right. Conceal exceptional speed and security of understanding. In my experience, if Jim cannot illuminate gently but vividly an issue you have raised, then that issue will be very hard to resolve. Next slide, please. Let me briefly discuss this example, which is known to a few people here. Julia visited Yale, I think, 40 years ago for a semester, and it was a very important occasion. A lot of things happened. She was also a very good babysitter for my youngest child, Duncan. She referred to him as a sink of charms. He still is, I would say, although he's more difficult now. But so a group of us, Julia, Dave, Jim, and I, gave a lot of thought to recursive saturation, Scott says, etc., with much emphasis on its role for PA. And I tried and failed to understand if there were any non-trivial recursively saturated structures generated by indiscernibles, and leave any of it vague. In fact, how great was my lack of insight? Probably the next time I saw Jim, he told me, to my amazement, that all recursively saturated structures, suitably understood, could be generated by indiscernibles. I found this genuinely amazing. He used, of course, difficult work by Nesistro and Rödl. Next slide. And then before I get on to the mathematics, I want to thank him for being such an admirable example of an exceptionally gifted mathematician who so courteously shares his gifts with others. I want to thank Roman, also a deeply admired longtime friend, for arranging this meeting where we wish Jim a happy 85th birthday and good health for him and Sue. Next slide, please. Okay, so Jim and Roman have published an admirable book on models of arithmetic. I've got it here on my desk. I'm very proud of having been an editor of the Oxford Logic guys, effectively. Very, very strongly recommended that book. And I think it is a really wonderful book. Now, Paolo d'Aquino and I wrote a long paper, not yet published, although many parts of it have been published, inspired by an innocent question of Zilbert on the structure of definitions and quotient rings of models of arithmetic. Our paper is concerned with algebraic matters and uses little of the techniques used by Jim and Roman, but somehow I keep seeing our work as fitting naturally with that of Jim and Roman. I remember being in a restaurant with Jim, I don't know when it was at least 15 years ago, it may have been 20 years ago, when he mentioned, well, when I said restaurant, it may well just have been a bar, but when he mentioned aspects of our work about primes and was complimentary about it. We've now gone much further, and I present below a brief summary of where we have reached. So most of a long paper has been written, and we have published several papers that emerged from our work. The long paper was held up by unforeseen circumstances. Next slide, please. So let me pass over this quickly. I mean, The way I look at it, when we start doing non-standard models of PA, it's Paula and I, most of the basic algebra from Euclidean division comes in immediately. Just it does, just as one does it, one learns it at school. So definable ideals are principal, etc. And we work only with principal ideals and mainly prime ideals. In this context, the same as irreducible, same as maximal, with an obvious unique factorization, of course, involving some kind of coding. All of this known from the 1930s. Much of it can be done in natural fragments of PA, but we do not pursue this here. We assume we have a sensible exponentiation on the model of Earth. Next transparency, please. Next slide, please. Oh, okay. The primes are cofinal in M. That's not difficult to prove. And much deeper facts are known about distribution of primes. I won't state them because they are actually some of them are very complicated, but very important. So if M over a prime P is countable for P non-standard, the residue ring cannot have both plus and times computable. I proved that a long time ago, around about 1978. I was trying to figure out something to speak about it, maybe at the International Congress for History, Logic, and Methodology of Science. And also I'd been reading and listening to all the praise about Harvey's paper on initial segments of non-standard models of arithmetic, and I decided I had better do something better. And it happened that I knew a lot of number theory. Even during my philosophy days at Cambridge, I couldn't bear to go to most of the lectures, and I went to Castle's, for example, where I learned a great deal of Pierric stuff. And so I came into the later part of my long graduate career as sort of half mathematician, half philosopher. So I knew the tricks that would get one this result, and Julie got it, and people had liked it. So the M over Q, where Q is a power of a prime, are local rings. And then it turns out, and although, something surprises me, that people have not used X, Quotient, Yershoff, and especially X's later work, they haven't really used it in looking at the issue of models of axioms for the M over Q's, where Q is a power of a prime. See, this for me is one of the Axis paper is one of the most important papers in model theory for me. Axe, of course, was a very, very strong number theorist. And the all-important ingredient I was doing, what we do later, is Axe's work on the theory of finite fields, which depends crucially on two great theorems of 20th century number theory, Bayes' Riemann hypothesis for curves over finite fields, and Chebotaryov's theorem on distribution of primes. They were both proved, well, in the 20s at the latest. There is a very nice article by Lenstra on Chebotaryov. I would strongly recommend it. And I would say that, without Chebotaryov's theorem, we would not be where we are now. And it fits somehow perfectly with the definability theory. Both the theorems mentioned can be proved in PA, and really Axe's work shows that they controlled at least the algebraic model theory of PA, what we wanted to know. Next slide, please. Okay, so now for P standard, M modulo P is clearly isomorphic to FP, and there's nothing interesting at first glance to say about that. What do quotients by non-standard primes look like? Now, Axe showed that they are pseudo-finite fields in his sense, so they're connected, it's connected to the Riemann hypothesis for curves, but ultimately he showed that these are elementarily equivalent to ultra products by non-principled D on the set of standard primes. So the index set is a set of standard primes, but then you put on that index set, say, finite fields or general fields. So there's one canonical index set that plays a fundamental part in this. Now, this is rather deep. And those of you who have read, say, the X Quotient first paper on the Artin conjecture will recognize that they have seen this kind of thing before in connection with linking fields of power series over finite fields and non-principal and, excuse me, general p-adic fields. I mean, this is a, hello? Who said that? Oh, who said it? I don't know.
I think you can continue.
Yeah, okay. So we see that M over R for R non-standard is elementarily equivalent to some non-principal ultra product of various Z over P's for standard primes P, and conversely. Knowing the ultra filter gives one the M over R, and it would be natural in some sense to write this, the field you get as F sub D, where D is the filter. Next slide, please. Next slide, please. Now, for standard P, an arbitrary K in the model, the ideal P to the K is elementarily equivalent to an ultra product of various Z modulo P to the N. So M over P to the K is pseudo-finite, and it follows by a deeper argument already published in Fundamental that one can extend this kind of thing to much more general M's. And at the end, I'll tell the full story. But what about M over R to the K for R, a non-standard prime, and K arbitrary? So, well, next slide, please. The last paragraph doesn't matter here. The central equivalence in X Quotient shows that if we choose the non-principal D, then the ultra product of the QPs is elementarily equivalent to the ultra product, also with respect to D, of the polynomial rings in one variable over the FPs where P is standard. So it's a formal power series thing with a normalization. This doesn't seem to be noticed too much at the time. We were forced to look closely and get a formulation like this. Now, lack of time forces us to be very abstract, but various non-trivial functorialities allow us to show that the M over K are non-computable. I hadn't considered that in the early paper. But issues about plus and times are more delicate than they are for the Tenenbaum setup. For standard P, these structures are computable. Next slide, please. No, I think I'm making fairly good speed. Yeah. Most natural theories of quotients by prime powers are shown to be decidable in Axe's paper, with proofs spelled out in our existing manuscript. And they depend heavily on Axe's work. And in turn, they depend very, very heavily indeed on Chebotaryov's theorem. At the very end of his annals paper, Axe lists the problem, which then remained open for about 60 years. This is the problem of decidability. Hello? This is the problem of decidability. I don't know, somebody's interrupting me, but I don't know what it's. Can you hear me?
It's strange. Angus, it's strange. We hear you, and there is some slight interruption, but we don't hear it at our end. We just hear you.
Okay. So can you go back? Yeah, no, here I'm on the page. At the very end of his annals paper, Axe proves a lot of decidability results for various classes of the type we've been discussing, involving powers of primes and so on. And the last problem he raises is the most general, which requires totally different techniques. Namely, he wanted to know if you took big M's ranging, as we said, and we took little m as ranging over elements of M, and then you've got a quotient ring, which is certainly not in general a local ring. And we think out in the real world, it would be for the standard model, it would be a product of prime powers. Okay, but it's a bit more complicated because the notion of product is much more delicate in the non-standard ends. Now, in principle, we knew how to do it for a long time, but Jamshid Derakhshan and I had worked on this kind of thing for a while. And after 60 years of being open, we were able to show that the theory of the class is decidable. This is pretty hard. I mean, the proof is very satisfying. It's only 3 pages. And one hardly needs anything from Max Quotient except one basic result. Anyway, the surprising thing is that we used adelic model theory and got a very short proof. And adelic model theory involves products of the p-adics and things of this kind. And so our analysis depends on another classic, the Pfefferman-Vort theorem of 1959, combined with the various techniques of Paula and me, and earlier work of Jamshid and me on model theory and computability for Adel ring. Next slide, please. I think it's nearly done. In the Springer, there's a book, the Springer Tribute to Katrina Byrne, who is a Scottish woman who was an editor. It's published as Mathematics Going Forward. I returned to an old obsession of mine, namely whether the theory of an individual QP as a finer definability theory, in some sense uniform in P. You see, one of the things that not everyone is aware of, and people should be, is that the existing decision procedures for the p-adics are infinitely more complicated than that for the reals. I mean, the known bounds are very, very high, involving iterated exponentials. I've been working on this, and I think I've managed to get it down into finite bound, but I'm not entirely certain. So in my last paragraph, I say the following. To get to this new axiomatization, one uses Paul Cohen's work. Paul Cohen found a quantifier elimination, which is utterly brilliant for the p-adics, and it can be Jamshid and I could modify it a bit. Cohen led to Denef in terms of getting the structure of definable sets, cell decomposition, and so on. And then Pass and I did that uniformly in P based on pretty hard and pretty long geometric and measure theoretic analysis. Now, the rationality proofs of Denef, later refined by Pass and me, suggest axiomatizations that spell out for you certain things which we had known a long time after the work of, say, Denef. Namely, there are constructive recurrence relations in back of the quantifier eliminations for the p-adics, individual p-adics or uniform p-adics. And also, people tend to have forgotten, at least I don't see it mentioned very much, that there are very striking periodicity estimates in the theory of the p-adic fields and related things. So I worked on this for a long time, and in the Katrina Byrne book, I find new axiomatizations for both the p-adics and the quotient ring case. These aren't, well, there are proofs are given in the Byrne thing, but I think before we put this into our big paper, we'll have to do a little bit more work. So I'd like to thank you very much. I hope I haven't gone over too badly. My timer has gone on the blink. So how much time do I have left?
There is plenty of time, actually.
Okay, so I'm basically open for questions, or I can say something about individual articles. I mean, I imagine that we can prove a lot more about non-standard primes, and then you would get it for general elements, but we haven't really come upon anything very, very striking. Of course, there are things I did when I did the Tenenbaum thing. I published some of them, I think, or sketched proofs, but they involve very heavy number theory done by Magarius and Odlyshko and so on basically on error terms and Chebotaryov's theorem. And they're very important in mathematics. And it seems to me that what I wrote down then does give a proof of this numerical version. And that, I mean, is one of the fundamental theorems of number theory. So it ought to be of some use, but it's not entirely clear where we would go next. Of course, it would be nice to bring what we've done together with some of the beautiful ideas in the book by Jim and Roman. But if time permits, I'm happy to say, I think one or two sentences in this version are false, but mainly because of a typo. There's nothing, I forgot to add one word or something like that. The paper itself, the current paper, oh yes, well, maybe I can tell a story then instead. It's about Zilber, whom I enormously esteem. I've always liked him. I've known him. I knew him for a long time before I met him. We somehow occasionally managed to get communication. Then I finally met him at the Warsaw ICM. So when I had two retirements, different jobs, and when I finally left Reading or wherever I was, but I was basically in Oxford, I wanted to continue to be active, and the Leverhulme Trust in England has a very generous system of emeritus fellowships. I'd had one before, I think maybe from my previous retirement, but I tried them again, and I needed to, this was in 2013, I think, or 14 maybe, but I went to Zilber and asked him if he would write a letter for me. And he said, of course. And then he went away. And I mean, I'd written for him before, and he did write for me, and I did get the fellowship. But he sometimes has a very unusual sense of humor. He came to me later in the day. I think I was going maybe to Korea that night. And he said, well, I will write that letter for you, provided you solve this problem for me. Now, the problem has taken us about 20 years to solve all of them. And it came from some of his explorations in quantum mechanics about, well, I'll not go through it. I mean, he's quite partial to the use of a single non-standard element in a proof in physics to simplify it. And sometimes it's very elegant. But I don't think he's ever really published the paper. And he only wanted to know the following. You see, I think the words in which he stated it to me it's obvious to me that it was false anyway, but he took this through arithmetic, and he chose a prime. No, I think he needed to choose a prime which was congruent to 1 modulo all the standard integers. And you get these things, and in the non-standard model, and then you play a little game, and you do a little bit of non-standard abelian group theory, and there you are. But he wanted to know whether you could, in fact, interpret arithmetic in the quotient by this non-standard prime. Now, it's pretty obvious to us in general, Gödelian grounds, that you cannot do that. But he didn't really give any definition of interpret. And I think I went to Korea that night, I can't remember, but and I thought about it quite a bit. Then, in any case, I was not much interested in this particular problem because it seemed to me the answer must obviously be no. I hadn't had time to think properly. But I was interested in the fact that people had not paid any attention to the model theory of this class of rings, M over P or M over P squared or M over P to the K or anything like that. And that things were not so obvious as they might have thought. On the other hand, using interpretability, simple interpretability results about truth definitions and so on, you can easily show that the problem is not solvable. But I never bothered. There was nothing to check. I never told him this. And Then later, Tom Scanlon, several years later, after I gave an elaborate proof of much more difficult things, Tom pointed this out. And of course, this is true. So the problem was really not a very substantial problem. On the other hand, to give an analysis of the model theory of this class of rings is a distinctly non-trivial matter, and we needed Weis's conjecture, and we needed Chebotaryov's theorem and related things. So although I think this thing cost us 10 years of work on and off. Of course, we weren't getting to work together very often. We got one chance to work at Oberwolfach, but we didn't write quite as much as Jim and Roman wrote on their visit to Oberwolfach when they produced this very beautiful book. But we made a lot of progress on that, and I think the paper is interesting, but we're not getting much attention for it. Don't know quite why. And I also overheard in a logic bar at a meeting not too long ago, somebody very highly esteemed, and whom I esteem, making some remark about what's been happening in models of rhythm. He'd been to several of her lectures and so on. What's been happening in it, it's as if it's not somehow a worthy companion of other variants of model theory. But the thing is, it's very hard. You're not going to get anywhere in it unless you go and learn something of actual hard proofs. Proofs that, at the time that they and Chebotaryov did these things, these guys were very close to the best mathematicians in the world. They overtook Artin on this kind of thing and so on. But the paper will be finished shortly, and I'll try to make sure that it gets to the people who are linked into this. And maybe there'll be chances during coffee or something. So I don't think there are plenty of things I can say, but they may take quite a long time. So I think I just say thank you, and that's it. It was an honor and a pleasure. Thank you.